think the name, I'm happy to see the big crowd here, and I guess the name of the talk is probably one of the big reasons, so we'll see if I can come through and explain the question mark. First of all, I do want to say that, of course, I'm here. The reason I'm here this weekend is I'm getting an honorary degree from Waterloo, and I just wanted to say, I'm going to say this again tomorrow, but I want to say thank you to the department for this great honor. I know there's a lot of work involved in making these kind of nominations, and it means a lot to me, both from a professional point of view, because Waterloo is a great university, but also because I was a student here over 40 years ago. So it meant a lot. When I got the news, I was very, very happy. So I want to thank everybody who did sure a lot of work to make that happen. So, statistics, the new sexy. So I understood that, and I see there's a lot of students here at the talk, so to confess, one of the goals of the lecture is trying to encourage students in math and undergraduate students in science to take statistics courses and to consider a graduate degree in stats or biostats and a career in statistics. Because statistics tends to be sort of, especially nowadays with data science and machine learning and AI, it's sort of like it's downplayed maybe, and people don't think of it as an exciting field. So part of one of my objectives of the talk is to try to maybe to raise the level of excitement about statistics and what it can do. It's a hot field. At Stanford, and I think the case here in most universities, the enrollments are way up. The number of students applying to our master's and PhD programs is just incredible. And the graduates can find jobs very easily because not only in academia and pharma companies, which are the traditional places for statisticians, but now, at least in the Bay Area, pretty much every tech company is crying for statisticians. Google, Facebook, Twitter, and small companies. Everybody is getting data and they need to make sense of it. And statisticians are key players in that task. And if you're in academia, we also find that our PhD graduates can step right into a job as assistant professor, whereas in many fields, like in biology, you have to do a 3 to 5 year postdoc, and then it's still hard to find a job. It seems to be, stats is still a growth field. The number of faculty is increasing both in statistics and biostatistics. Other fields like biology, math, and physics are not nearly as well off. So many really smart people in math get a PhD and they can't find a good job. It's unfortunate. It's because the field's not growing as statistics is. So my own story is I was an undergraduate here in mathematics from 73 to 78. I started off in math. I found it too abstract after about second year. I was in doing topology and stuff. Immediately I was thinking, having to map everything back to the real lines. And this wasn't quite for me, this abstract mathematics. Then I started doing CS. At least at the time I found it was, of course, computers were exciting, but there's a lot of work involved in trying to save a millisecond here or there. So I wanted sort of a happy medium. And statistics was perfect. It was a mix of mathematics. It is a mix of mathematics and computer science in the service of science, right? We're trying to solve scientific problems using mathematics and computation. And that for me was a perfect combination. So I did a second major in statistics, went on to University of Toronto, and then on to Stanford to do a PhD. I worked at Toronto here for 12 years, University of Toronto, and then I've been at Stanford ever since. And another success story, my son Ryan was an undergraduate in math at Stanford, went into statistics, happily. I wasn't his advisor, and now he's an associate professor in statistics and machine learning at Carnegie Mellon University. So what is statistics? Well, first of all, the name is kind of bad, right? It sounds, you tell people at a party you're a statistician, it's like they run for the door. Like, what is that? Statistics sounds like, it's baseball scores or numbers, right? It's really the science of learning from data, right? And maybe our field should be called data science, and that term data science is now really taking a life of its own. But it includes statistics as well as a lot of other fields, artificial intelligence, computer science, to help to learn from data, okay? And machine learning is a field which has grown up sort of in parallel with statistics, which has a lot in common. And I'll talk about that a little later. Is statistics boring? Well, that's our problem, right? Well, a little story, the statistician and the scientist, they're both going to be shot, and each are granted one last request. So the statistician goes first. He says, he wants to be allowed to give one last lecture on his grand theory of statistics. At which point the scientist says he wants to be executed first. Unfortunately, that's our reputation. Okay. But the sexy part. Well, so Hal Varian, a chief economist at Google, almost 10 years ago, he said, I keep saying that the sexy job in the next 10 years will be statisticians, and I'm not kidding. So Google is hiring statisticians en masse, and they really, they understand the importance of statisticians. So here's the old section and the new section. So the top guy you recognize for sure, right? It's Tony. And now Nate Silver, right, has really brought statistics to the fore with his 538 website. So right, it was, I think first it was allied to the New York Times, and now it's a separate site, using statistical analysis to predict the outcomes of elections. In 2012, he did very well, like a lot better than most sites. I think he got he got the U.S. presidential election, the president right, and all Senate races. In 2016, like most people, he didn't get it right, but he was not wrong by as much as other sites. Maybe that's all I can say. And this book I recommend, he wrote recently, is very interesting, talks about some of the problems he sees in statistics and the application. So he's really used simple but careful analysis to do a much better job of doing predictions in elections. And I found this on the web. Let's see if this works. Oops. At least my wife says it's true, so I don't know. Okay. Okay, so the way background, I want to talk, the rest of the talk, I want to talk about an application of a method that I've developed with others called the Lasso and Sparsity, and an application to a real problem in healthcare that I'm currently involved in at Stanford. Okay, so I'll give you an idea of a new way of doing statistical modeling, fairly new, and also an application which I'm quite excited about. So, and again, if it's feasible, if you guys have questions during the talk, go ahead and ask. And if I'm overwhelmed with questions, then maybe we'll stop. But for now, at least if it's a question of something's not clear, please let me know. So the Lasso for supervised learning. Well, supervised learning is a term that the machine learning people coined, which I think is very good. You're trying to learn from data. You have some features X, and you're trying to learn them from, you're learning a response variable, some kind of measurement from a bunch of features. Okay? So I have P features on a case, on a person, and I'm trying to predict something on that person as a function of these features. And these weights I'm going to find the best set of weights to make the prediction. And that's called supervised learning. And the Lasso is this particular way of doing supervised learning. So I have trained data on n cases, the response variable and the features. I say that here. Before we get to the Lasso, the traditional way of doing supervised learning is least squares fitting, right? So I find the beta 0 and beta j, these weights, to make the sum of squares as small as possible. So I try to make the errors in the predictions of y as small as possible. Find the weights to make this a good as fit as possible. This won't work when p is bigger than n. Well, it doesn't work because it's a singular system then, right? The weights are not unique anymore. It'll overfit as well, right? The error will be exactly 0, but the model won't be very useful. Okay? But this, of course, has been around since the time of Gauss. Right? Least squares is sort of the bread and butter method of statistics. Well, the Lasso makes a change to that. It adds something. It adds a constraint. It says we're going to make the fit as good as possible, just like least squares, with a constraint that the sum of the absolute values of the coefficients is at most some bound, some budget. So think of it this way. We're going to do an optimization, but I give you a budget on the total sum of the absolute values of the weights. So if this budget is very large, you're going to go ahead and just do least squares, and you're going to get maybe a perfect fit or a very good fit. But if I make this budget smaller and smaller, you're going to have to, if you are the optimizer, you're solving this problem, you're going to put the non-zero betas where the features are most predictive. And if a feature is not predictive, you're going to give it 0 weight. You're not going to spend any money on the features that are useless, right? So the Lasso does that in a formal way. It's a convex optimization problem. For a given bound, we solve this problem. It's a convex optimization problem with a unique solution, okay? And it gives you what's called sparsity. So if the budget is low enough, some of these weights will be exactly 0 on the features that are not useful for the prediction, okay? And this is also, I say it's convex. If you know something about convex optimization, this is a very good thing. It means the optimization can be done very efficiently for very large problems, like the number of variables can be in the hundreds of thousands, the number of observations can be in the hundreds of thousands, and you can solve this on a scalar computer. Okay? So what is this about sparsity? Here's one more,
here's a picture of what's going on. An alternative to Lasso, which uses absolute value budget, is what's called a ridge regression. This has been around since the 70s, which uses the sum of squares rather than the sum of absolute values. This absolute value gives you what's called sparsity. In other words, when you run it, when you solve that problem for a low budget, it gives you some exact zeros, which is a good thing because it means you can throw those features out and not worry about them. Okay? Whereas if you use the sum of squares, it makes a lot of the weights small but not zero. And here's why, pictorially, if you like geometry. Here's the overall least squares estimate, unconstrained. Here's where this budget is less than S. It's this blue circle, right? Here P is 2. I have 2 variables. Here's where the sum of the squares of the beta is less than some number. That's the radius of a circle. So in other words, the ridge regression is saying, find me the first place that these contours of least squares hits the constraint region. Because this constraint region with sum of squares is smooth, you're not likely to hit at a place where one or the other is 0. That's here and here, right? You have to, actually, it's probability 0 that's going to happen. But move over to here, where all we change now is the sum of the squares with the sum of the absolute values. That's a diamond. It has corners. And the contour can quite easily hit a corner. That's a 0, right? There's where beta 1 is 0. There's where beta 2 is 0, right? And high dimensions, that diamond becomes like a polyhedron. If you hit along a corner or an edge of that polyhedron, you get zeros. So the absolute value is not a smooth function. It's got corners, and that's what gives you sparsity. This is a really good thing, because it means you can do supervised learning with a Lasso for many, many features. It'll throw out maybe 3/4 of them and say, these all have coefficient 0 because they're not useful, and these other ones are the ones that are predictive. Okay? Maybe I'll pause for a question, because this is the one technique I'm going to use in the whole talk. So don't be shy. If you haven't seen this before, it may look mysterious, but does anyone want to ask anything? You have a question. Oh, well, that's because you rein in the coefficients. Okay, so coefficients are like cattle. Turned out it was a really good name because there's a lot of, like, this field's taken on a life of its own. There's 50 flavors of Lasso, like adaptive Lasso and group Lasso, and it was a good choice of name, turns out. So, okay. So this picture is just a way of explaining, saying a little more about this optimization problem. And then, I won't get into details, but the budget you pick, you do so it depends on the problem, right? If you have very high signal in the problem, you're happy to take a big budget, right? Because then you can fit a lot and grab some good signal. On the other hand, if the signal to noise ratio is very low, you want a small budget because you don't want to overfit. So we use what's called cross-validation to pick the budget. Just in words, what you do is you take the data, you divide it into like 10 parts. You fit the Lasso on 9 parts, and then you see how well does it predict the 10th part. You do that for every part in turn, and you vary the budget to see what budget gives me the best prediction out of sample, right? And that makes sense. Again, there's no one budget that will work for every problem. It depends on the data. So that's why you use internal validation to pick the budget. Okay? Okay. Well, here's an example from one of my papers or a book of, this is prostate cancer. We're trying to predict actually the log PSA on, these are men whose prostate was removed for prostate cancer surgery, and there were 8 features, and here's the Lasso, here are the coefficients of the Lasso. Here, the shrinkage factor is 0, so the Lasso is completely shut. Everything's 0. And as we relax it, we move to the right, eventually getting to the usual least squares estimates. But in between, you see there's a lot of things are 0. Like at this point, only one guy is non-zero. At this point, the point chosen by cross-validation, we have 3 non-zero coefficients. Now the rest are all 0. So you see the sparsity in this picture, because a lot of the coefficients are lying at 0 until at some point they eventually become non-zero. Okay. So, and some emerging themes from this work is that these L1 penalties now are used in a lot of different places. I mean, a lot of other people have worked on this as well. And they're a natural way to enforce sparsity. And with large data sets, sparsity is really important, because we can't estimate a regression model on 1 million variables unless we have 100 million observations. Unless we assume the model is sparse, so that only some of the features are informative. With sparsity, you can get away with a lot less data if you assume sparsity. And I won't go into details, but just if you want to read about this later, the computation is the fact the model is sparse makes the computation much faster too. If you have a million parameters and you only end up with 100 non-zero ones, you can imagine that you can bootstrap that fact and you can exploit the sparsity to make the computation much faster. Okay? And there's a lot of a big, long story there, which I won't get into today. But these are my two long-term collaborators and friends. We've written a package. Actually, this is kind of funny in Fortran, where I learned Fortran here at Waterloo, right? And people still laugh at me when they hear, "You're programming in Fortran?" You know? But Friedman is a master Fortran programmer, and so he knows exactly how to arrange the computations. And Fortran can be as fast as C or other things if it's done properly. So this package in Fortran is extremely efficient, and it's used by groups around the world. It's in R. It's an R package that's calls Fortran. There's a lot of computational tricks to make it fast. It's called GlimNet. Do I say that somewhere? Yes, GlimNet. So if after this talk you want to learn more about the Lasso, and use R, just go to R and look at the package GlimNet, and that's all the things you'll see today computationally done in the GlimNet package. Okay. So, and now on to the application, which I want to tell you about, which is a recent collaboration. How many units of platelets will Stanford Hospital need tomorrow? Okay, so this is a joint collaboration with this Ta Pham is the head of the Stanford Blood Center. These are pathology residents and two of our graduate students in statistics. And my friend and computational expert Naris has done the deployment of the software, which is important. That's another thing I want to sort of make clear. Computation is so important in statistics, not just as you do research and you figure out how to do things, but also when you publish a paper and you want people to use what you're doing, you have to have good software tools, right? Because nowadays there's so much stuff produced that if you don't have a good software tool, people aren't going to bother. People aren't going to take the time to program up your method. So if you have something you believe in, spend time making good software and supporting it. It's a key way to transfer your ideas into actual practice for other people to use it. So I've spent a lot of time in my career more and more on software development because it's so important. And this paper in PNAS in the last 4 months describes what you're going to see right now. Okay, so here's basically, so the head of the Stanford Blood Center came to me and said, no, I have a problem that maybe you statisticians could help. The Stanford Blood Center, at Stanford is a fairly small place. There's a blood center and there's a hospital, and there's one blood center that supplies the hospital, that's it. Whereas in Toronto, you've got many blood centers, many hospitals, but the basic problem I'm talking about does apply like everywhere. But the configuration of Stanford is particularly simple in the sense that there's one blood center that supplies the hospital. And platelets are one thing they supply. I had a picture of platelets here, this bag. Oop. It's like this, here's a bag of platelets, 1 unit. Okay, it's this yellow liquid. It's very precious. Okay, if you've ever given platelets at a blood donor center, it takes about an hour and a half of your time, unlike whole blood, and you can only do so about once every 1 or 2 months because it's your body. It's not good for your body to give too many platelets away. And furthermore, so the real challenge here is they have a 5-day shelf life. So most blood products are good for 45 days or so. Platelets are good for just 5 days. They can't be refrigerated. And the first 2 days are for safety testing. So there's basically 3 days of use, and then they have to be disposed of. They're no longer safe to use. Stanford, so what happens now is Stanford Hospital calls up Stanford Blood Center every evening or sends them an email and say, well, I think we need 40 units tomorrow, or 45 units, or 35 units. It's about that order of magnitude. And they make that guess is based on sort of, it's a guess. They see who's in the hospital, how many units they have on the shelf, what surgeries are planned tomorrow, but it's a rough guess. And they don't want to run short, because if they run short, it's pretty bad. They have to buy blood from some other blood center on short notice, very expensive, difficult to do. So they tend to over-order, naturally, right? And they waste about 8% of the blood, or 1,400 bags per year, which is that's a lot of resource. So the head of the blood center asked me, can you come up with a statistical system somehow to make this waste less, without any shortage? Can we do better? Okay. Well, Oh, see, here's some overview of the data. This is, what do we have here? This is, well, two years of data. This is the consumption, number of units. Every day it's about, average is about 35 or 40. This is 3 days. 3 days being important because, again, there's 3 days of shelf life. Okay, and there's some further plots. One thing you'll notice, which we'll pick up later, is that the number of units on the weekend is much less that's used, which is kind of obvious because there's fewer surgeries on the weekend. Okay. So the idea is here, they said, well, we have all this data. Like in the hospital, we know everything. We know we have all the CBC and the records of patients in the hospital. We know what surgeries are planned. So there's a lot of good information about the hospital. So we can use that information to predict how many units the hospital are going to use for the next 3 days. Of course, not everything is predictable. If there's a car crash the next day that requires 15 units of platelets, that's not predictable. But a lot of it is, I think maybe 70% of it is predictable to some extent. So the information we have was the CBC count for all the patients, census data, which is which patients are in which wards, when were they admitted, what surgeries are planned, et cetera. I think a modern place like Stanford would have their databases in great shape. Where you go in there and you just, please give me the data and it's all coordinated. Well, that's another thing you'll learn as a applied statistician. A great deal of your time is spent on just cleaning up the data. It's like, at first it's kind of depressing. Like, why am I doing all this? But you realize you have to do a good job at that in the first part to get the data in order, to clean it up, in order to have any hope of doing a good job in the modeling phase. So if you become a statistician or you do data analysis, don't worry that you're spending a lot of time what seems like it's on drudgery. It's important, and we all do it. So here was a case where things, again, a modern case like Stanford, our place like Stanford, our first thought was let's do things on a per patient level. You know, John Smith's in the hospital. Which ward is he in? What surgeries are planned for him? How much blood is he going to need? We couldn't match. The data were like in 3 different databases. We couldn't match the data from the different databases. It was a lot of it was missing or wrong. It was just an absolute mess. We spent a lot of time trying to figure out how can we accumulate information on one patient. We couldn't do it. So eventually we backed off and said, let's just work on a per hospital level. So for the whole hospital, we'll create the features not per patient, but for the entire hospital. Okay? So I said that we first tried to work on the patient level, but it got to be too much of a mess. It wasn't practical because the data was not in good form. And again, this is the case in, unfortunately, a lot of information systems in our modern world are just a mess because, for various reasons, because they've been there for a long time, or there's more than one system like here, and they don't talk to each other properly, and they're not matched. So we ended up using features at the hospital level. So CBC measurements for day I and feature J, the number of patients below the first quartile. So we said, well, if there are patients who have a low CBC count, then they may need a blood transfusion. And then how many patients were at each ward for each day, and a lot of other features. Here's more of them. How much blood was used the previous days? The surgeries, day of week information, 61 features in all. So for each day we have 61 features, and we're trying to predict how much blood is going to be needed the next 3 days based on the 61 features we know in the hospital. So sitting here today on Thursday, we have these 61 numbers, and now can we build a model that predicts for the next 3 days, Friday, Saturday, Sunday, how many units of platelets the hospital is going to need? Okay? That's the goal. So this notation, this is always hard to parse when you're looking at a slide, but YI is what we're trying to predict. The actual platelet usage on day I. This is the amount that arrives on platelets that arrives on day I. Number that remain, the waste, and the shortage. So again, the goal here is to have no shortage. So to come up with a prediction and a plan that means we order enough, there's no shortage, but we want the waste to be small compared to the current waste of about 1,400 bags a year. Okay? So here's in low-tech graphics, here is what we're going to do. So we're sitting here at day I. we're going to train a model. So we have 3 years of historical data. So we're going to use the 3 years. We're going to use the past historical data to build a model which predicts, based on the 61 features, how many units of blood we're going to use the next 3 days. Right? And we have that information. We know how many were historically were used the next 3 days. So each day we're going to look at the next 3 days, and we're going to train a model to get the best weights. And then we're going to use that today to predict how much we're going to use for the next 3 days. Okay? And then we'll use that to try to figure out, to try to tell the hospital, here's how much you should order. Okay? So it's got to use information on how much we're going to use, how much is on the shelf. That together we can use that information to figure out how much to order. So the question was, I said, I had a guess that the amount that was predictable was about 70%. I don't know quite where I got that from. Anyway, and then your question was, does the model take into account the other 30%, which would be things that aren't predictable, like car crashes? No, it doesn't. So as you'll see, we put in a buffer of about 5 or 8 units to try to take care of that. But there's no real way to, I mean, it's not predictable, so we don't have that information. But the result of the fact it's unpredictable is that we put in a little a buffer. So if the prediction's 40, we might to order 40, we might order 45, just because of that, things we can't yet predict. Yes?
Can you predict the volume for 2 days and then use your wastage for the third day instead of having the wastage be actually wasted?
So the question is, can I predict the volume for 2 days? And what was the second part?
And then your wastage becomes overage for the third day that can be used instead of actually being wasted.
No, well, I mean, we are going to use the only thing we waste is something that's 3 days old and is unused. So the model's going to use, it's going to use, if a bag's unused in 1 day, we're going to use it the next day. Only if it's unused at day 3 do we throw it out.
Right, by predicting the volume for all 3 days, if you get it wrong in an overage way, you waste bags on the third day. But if you predicted only 2 days at a time and only ordered enough platelets for 2 days, then the overage would still be usable on the third day and could be deducted from your modeling for the production on the middle day of these 3 days.
Okay.
To reduce the wastage.
So I will, I have trouble parsing that. So let's take that offline. So
sure.
You might have some, so the idea roughly was, I think, just rather than try to predict all 3 days, predict just 2 days and use that to your advantage the third day. And I have to think about whether we're doing that. But okay, yes, another question.
Does the prediction change with seasons, such as winter or accidents?
Well, let's see. The model is going to be retrained every week, so so it will change with season, but that will happen just automatically, right? Because we trained on the recent data. Yes. There. Other questions? Yes.
Do you take the time series nature of the data into account? Like you have weekend is unknown, so into which day it is.
Sorry, time series nature into
account in your model, because there's weekday or weekend.
Yes, well, so the question is, we take the time series nature into account. There's weekdays and weekends. Weekday and weekend is one of our features. So as well as the previous amount of blood that was used in the last week. So that's all accounted for by the features on the right-hand side. Okay, so that hand drawing is now just sort of fleshed out into more. So we built a supervised learning model using the Lasso to make these predictions. I tried other techniques like random forest or gradient boosting, didn't really help because the data is pretty small here, roughly. We started day 200, we trained the model. So we had 3 years of historical data. What we did was we trained it in the first 2 years, rolling it forward, and then we looked to see how well does it do in the third year. So we have historical data, we want to use that third year. This is not all kind of details, but basically this says how much we're going to order is how much is left over, minus how much was ordered previous days. And it's just simple accounting, basically. Okay. Now, so I have a little confession. I'm not going to tell you what. So this was our first technique that works quite well, using the Lasso. It's not quite what we end up doing, because for the kind of intuitive reason that the Lasso uses a loss function which is symmetric, right? Squared error. But if you think about it, this problem is not symmetric. It's a lot worse if the estimate is too low than too high, right? If it's too low, you have a shortage. If it's too high, you have some waste, but that's not so bad.
So the fact it's not symmetric means actually you don't want to just use something as simple as the lasso. You want to actually design something more tailored to this problem. So I won't go into details, but you can read about it. We actually set it up as a sparse decision problem to minimize the waste subject to no shortage. Okay, so we turned it into what's called an LP, a linear program, that posed the problem in a more direct way and took into account the fact the loss is not symmetric. Results were a little bit better and more interpretable. Okay, but that's much more detail that I can convey in this talk. But just to say, as often is the case, your first idea works pretty well, but you can make it better. In this case, making it better was acknowledging the fact that the loss is not symmetric. Okay, so what happened when we fit the model? Well, some of the features that came out were intuitive. I mean, the day of the week, as I mentioned, was Friday -3. So this means we're not going to use as much on the weekend. If we're predicting on Friday, we don't need as much for the weekend. That's clear because the number of surgeries on the weekend is a lot less. Whereas Sunday, it seems to be, there's a lot of surgeries in the early part of the week, Monday through Wednesday. Other things, you can't really parse these, but what came out was things like hematology, which uses a lot of blood products. There are a lot of patients in hematology with surgeries planned in hematology, it would give more weight, etc. So most of the weights and the features that came out were intuitive. So what happened was, so how did the model do? So again, we trained the model for 2 years, historically, and then say how well would it have done in year 3 if we used it, compared to the actual usage. And what the overall result is quite nice. The shortage is reduced from 8% to 1.85%, so a reduction of over 3/4. The number of bags was, I think, was 1,500 wasted before, and now it's only 359. So it's really quite impressive. And the reason is, I mean, there's a lot of good signal here. This is a very predictable situation. Not totally predictable, but there's a lot of good information. If you use that information in a strategic way, you can get big gains. So what do we see here? Well, here's the time going along here. Here's the consumption in red, remaining in green, and the waste. See, first of all, you see that the remaining never goes below 0. There's no shortage. How close does it get? Maybe to about 5. That's the worst time. And the waste is, well, there it is. Sometimes it's 0, but it's never more than about 25. But overall, the waste is reduced quite substantially with no shortage. Not even close to shortage. Of course, there's no guarantee there's no shortage, right? Because again, there could be a plane crash or something, and then the next day, and then whenever. You can't predict everything, but you can only with high probability assure there's not going to be a shortage. And here's another plot of here's the number that transfused. Here's a cumulative plot. Here's what's happening now with the current ordering schedule, and here's what would happen if we use the supervised learning algorithm, the Lasso. You see the cumulative waste is much less. Sorry, this is the cumulative units of blood. Right. Okay. So, to summarize the analysis, the reduction about 8 to a little below 2%. My pathology colleague says that'll save Stanford Hospital this much, $350,000 a year. And I don't know where they got this number from, but they said it could save the U.S. healthcare system $110 million per year. I mean, just because again, this happens in every blood center. And I have colleagues in Toronto who work here, work at hospitals, and they have the same problem. And we've been talking to people now, at St. Mike's, that they want our software to see if they can implement it in their hospital. So the idea would be now, let me get a little ahead of myself. So the system is being deployed right now at Stanford Hospital. This is in the last week we put, this is a Shiny app, an R Shiny app, which the pathologist, the head of the blood center has at his computer. And every night he'll basically, put in the information. It pulls the features from the Stanford database, and it runs the optimization and says you need 43 units tomorrow. Okay, so that's the idea. And so the bigger idea is that we're going to distribute the R code around North America, and a center that wants to use it has to train it on their own data. Right? 'Cause every hospital has their own way of doing things. Their patient populations are unique. The MDs, the practice guidelines in every hospital are different. So you want to train it on your own data, your own patient population, your own doctors, and then
hopefully it can be used in a medical center or a blood center and reduce the waste of blood. And also, it's kind of funny, what's happening is my colleagues in pathology, or the blood center, they're very excited about this. And they say, we want to put it in place right away and let's just use it. And I said, hey, wait a minute, right? We've done one test of this on 3 years of data. I'm confident it's pretty good, but what I don't want to happen is they put it in the hospital, they start to use it, and it screws up, right? Because like it says you need 25 units and you're 10 short, because then people say, I never trust those computers, right? And then the whole thing is going to be wrecked. So I said, let's put it in place and have it run in parallel with the humans for maybe 4 months. And just confirm that it's doing a good job. At that point, then we can think about having it deployed to the hospital for the actual ordering of blood. And this is only one resource in the hospital that has this kind of problem, the fact that it expires. And they're hoping to use this kind of strategy to reduce the waste of other resources. And that's the shiny app, I mentioned that, okay. I won't talk about that, but let me just say, sort of as a general higher level wrap up, yeah, so my collaborators are very excited about the potential for this classifier to improve patient care. And again, this was, it really wasn't too hard. It was the application of a model, a Lasso model with some optimization. The hardest work, as I mentioned, to say it again, was to get the data into shape. Basically, because the data, as is often the case, is very messy and dirty and incomplete. And what I really want to convey is that this can be a lot of fun, very fulfilling. It's challenging. Trying to solve the problem is challenging. You get to work with smart people in other fields, and you hopefully have a positive effect on public health, which is a very nice feeling. So that's why I love statistics, and I hope I've conveyed some of that love to you today. And this is one self-promotion, but it's okay because this is a book that I wrote with colleagues recently. It's free online, so that's why I don't mind plugging it. The PDF's online. It's a nice sort of book for senior undergraduates or a master's level book that talks about supervised learning and statistical learning in an accessible way, and it uses R as the language. And we have an online course at Stanford that's also free that covers this book. So if you're interested in learning more about this field on your own, you can look at the book or the online course. So I think that's it. Happy to take questions. Yes, sir.
Is the ordering of the platelets given so that if you order X units for a couple of days, you're going to get X units? If you get X minus 2,
yeah.
So it builds in any kind of hoarding feature in the supply?
So the question is, the ordering, so if I ask for X, do I get X?
Yeah, is it built on that?
It is. I think that seems to be the case, because if they need X, the blood, and they don't have enough, so the blood center has a supply as well. But if they don't have enough, they can call blood donors in on short notice and they can get X. It seems like that's a safe assumption, that if you order X, the blood center can deliver X. Yeah. Yes?
So you had that sort of app for the doctors or whoever's ordering the blood, right? And you're saying, like, they're not putting in the features here, right?
Right.
You said that it pulls the features automatically.
Yep.
But previously you said also that the database of the features is extremely messy. So did you have to teach them how to input the data in a way that wouldn't have to be manually fixed?
So the question, I said that the data was messy and had to be manually fixed. Actually, my software engineer or colleague, he wrote scripts to do it automatically. So it's a lot of work, but he basically wrote scripts that would clean up the data automatically. And that was a lot of the work in this project. Yeah. Yes?
So even if your software doesn't work perfectly, doesn't this just push the problem to the collection, right? Because they can't store it any more than you can store it. The platelets, once removed from the person,
Yes.
clock starts ticking.
Yes.
They can't use them right away. So if they need an emergency now, you can't collect it because it takes 2 days to test it, right? So they still have the same problem, right? So even if you know how many bags to order from the people who collect the blood from
And the people who collect the blood, they know their inventory, and that's being taken into account here. So they see if they've got 10 on the shelf.
So the number ordered is, yes. So I'm not quite sure your question.
But, so, I guess like, I'm not sure why the issue is how much should the hospital order from the people who collect the blood, rather than the issue being how many donors will you need today in order to get the number of platelets you'll need 2 to 5 days from now.
So both are important issues. The first question is how much is the hospital how much does it need to use? And the blood center has to use that number on top of all the other things you have to figure out how many donors to get. So both problems are there. The first one was figuring out just how much is the hospital going to need to use. Yeah.
Sorry, Rob?
Yes.
I'm going to interrupt you for just a moment.
Okay.
I know we could probably go on for another half an hour or
Yeah.
so.
Are we? Okay.
But we have a phenomenal group of people today
Okay,
to
so-
speak.
okay.
And so what I'm going to do is throw a carrot out, though, because after our next speaker, we have about a 15 to 20-minute window where we intentionally built in you can come up and speak and ask questions individually of the speakers. So there's a little bit of a networking time. There's a little bit of a question and answer where you get to speak with
I'll
each
be-
one.
sure.
So if you join me in thanking Rob Tibshirani.